Hey everybody. We're now starting to look at how we can analyze pedigree charts to actually get some useful information out of them about the disease or the trait we're looking at. So here's an example of a pedigree chart you might be given. Obviously there's lots of information in here, and this is showing 1, 2, 3, 4, 5 generations of this family, and it's following a particular trait through those generations. So the big question that we're learning about firstly is this trait dominant or recessive? That's the first skill you need to have when you're looking at a pedigree chart. Okay, and there's two particular patterns to look for that are the big giveaway. So first of all, if a trait is dominant, then this is the pattern to look for. This is how we can prove that a trait's dominant. So if two parents that are affected by the trait, if they have an unaffected child, then this trait has to be dominant. And the reason for that is if the trait was recessive, then two affected parents can never have an unaffected child. And let's prove that with a Punnett square. So if we have a trait here, and one of the parents is recessive, let's use A's for our trait here. If one parent is recessive, homozygous recessive, and the other parent is homozygous recessive, that's the only way for these parents to be affected. They have to be homozygous recessive, and that means all their children are going to be homozygous recessive as well. So they'll pass this trait on to every single one of their children. Which means that this case here can never happen. This child here can never happen. So if you ever see two affected parents having an unaffected child, we've definitely proven it's dominant. And this is what it means. So if it's dominant, then these two parents have to be carriers. Each one is carrying one of the faulty dominant alleles. And now if we do the Punnett square for those two, they each have a big A and a little a. The big A is the faulty one because the disease is dominant. So one of their children, there's a chance their child is homozygous dominant. Then there's a 50% chance their child is heterozygous dominant. And then there's a 25% chance of having a healthy child. All the other options are unhealthy because it's that dominant allele that's causing the disease. Okay, so keep an eye out for that pattern. The other pattern to look for is the opposite, basically. So if you have two unaffected parents, and then they suddenly have a child who is affected by a disease, then that proves the disease is recessive. So if two unaffected parents have an affected child. And the reason for that is if the disease was dominant, then two unaffected parents, they can't have an affected child. So for example, if we have a dominant disease, then the only way to be healthy with the dominant disease is to be small a, small a. Because as soon as you have a big A allele, you have the disease. Or you have the trait, whether it's a disease or not. Doesn't really matter. So if a disease is dominant and you have two healthy individuals, they both have to be homozygous recessive. And so all their children are going to be homozygous recessive, and there's no way they could have an unhealthy child. So the only way for a disease to appear when both the parents are healthy is if that disease is recessive. And the specific way that that happens is shown here. So both parents have to be a carrier of that disease, which means when we do the Punnett square to show the inheritance, most of the children will be healthy because a recessive trait is only shown if you have 2 copies of the faulty allele. So that's the pattern to look out for if you ever... So that's the pattern to look out for to prove that a trait's recessive. It appears when both the parents were healthy. So if you can recognize those 2 patterns and prove it using Punnett squares and using some logic, that's how we can figure out the type of inheritance. So let's go back to our original family. We're keeping an eye out for either of those 2 patterns. So we have the trait here being passed from one father to 2 of his daughters. But there's no examples of our definitely dominant or definitely recessive cases. So sometimes you can't prove it. So in this example, we can't actually prove either way. But there's a last point to make, which is to say which one's more likely. And in this example, we have the trait being seen in every single generation of the family. So all 5 generations. And if you see a trait in every generation, it's more likely to be dominant than recessive. We can't prove it for sure. Traits are seen in each generation. It's likely to be a dominant trait. It still could be recessive, but it's more likely dominant because that means that it's just one particular dominant allele, like a big A, being passed down to the 2 children, then being passed down to more children, and so on. But if it was a recessive trait, that would mean... If it was a recessive trait, that would mean that each person who's married in from outside of the family or had children from outside of the family, each one of those has to be a carrier every single time. And that's pretty unlikely that every single one of these 4 people are carriers. But it could happen. Okay, so we've got our 2 ways to prove dominant and recessive, and we've got a way to say whether it's likely or not.